So this is another lecture that Chris and Wes made a while ago, originally made by these two guys who created the Micro P2 course. And so they made this, before they made the Micro P2 course, they were both Pi's for me and Micro P1. Anyway, these are a kind of a summary of a lot of the keywords that are reserved in C that you don't want to use for anything because they're kind of already used. We've seen some of them. We've seen character, we've seen case, switch, long, else, if, int, for, float, short, a couple others. Some we haven't. Vol is going to be a key one that we're going to talk about mostly today. Okay, so volatile. We're going to need volatile because the compiler doesn't really understand about things happening in configuration registers. It doesn't really understand the peripherals. It doesn't understand that when an interrupt happens, it can change values somewhere. And so you got to kind of tell it that I know you might think this value is a constant, never changing, because you don't see it, but it is going to change. Maybe it's an input from a port. So it doesn't know that there's a port value input that's going to change. So we use this keyword volatile to tell this, hey, don't simplify something away when you're not really sure what it does. And so we'll be using that for memory map peripheral stuff. That's again like the configuration. Well, that's I/O ports, either EBI type or other kind of I/O ports. And for variables that get modified by interrupt service routines. This is something that you're going to see probably in your lab, I hope. Okay, so again, if the compiler doesn't know something that is going to change, it's going to, well, do as much simplifying to make it disappear. It'll either just never look at it after it's assigned a value. That's probably what it'll do. After it assigns it a value, it'll never look at that again because it doesn't expect that to change. And also, if you do take Micro P2, these two, well, this case right here, you'll see in multi-threaded applications, global variables will also need this volatile keyword. And inline assembly, we already saw that the SEI instruction, we saw that in the inline assembly, it had the word volatile. So that it doesn't, it didn't disappear, even if maybe it doesn't appear to the compiler that it should exist. Okay, so here I want to show you an example. So again, Dylan, help me if you think I'm saying something not quite right. Preg, that asterisk says, hey, this is a pointer. This is a pointer to an 8-bit unsigned int value. And the pointer is 4744. So 4744, I'm given this a name. It's called preg, and it's at address 4744. So location 4744 is called preg. Okay. Now, if I had a little loop like this, while what preg points to, again, location 4744. So it says, is the data at location 4744 not equal to 37? As long as it's not equal to 37, keep in this loop. And someone asked, do I need this casting? And I believe that if you don't do this casting, you'll get a warning. I don't think you need it. But people that know better than me said, it's always good to do something like this. This is again reminding this guy right here that this guy is a pointer and it's pointing to an unsigned 8-bit integer. But again, I don't think we need any of that. It should work fine. Okay, so this, we might think, hey, this is going to work fine. It's a really easy thing. We have a address 4744. Is it not equal to 37? But the compiler is going to say, hey, the data at location 4744, if you don't tell it to change, it's always going to have the same value. So I'm going to take that to mean never get out of that. Never get out of that loop. And so let me show you the assembly language that will be generated or something like this for this declaration and this while. So this says, and we know these assembly language, load what's in location 4744 into register 24, and then compare what's in register 24 to the 37. Well, that's exactly what we're saying here. Compare what's in register 3744 to, or 4744 to the number 37. But then, branch if not equal, program counter is this line right here. -1 says, okay, if it's not equal to 0, go back to this line. So you see a problem with that? This line doesn't look for a new value at location 4744. Again, maybe location 4744 is an input port or some RAM, I don't know. Whatever's there, if it never looks back at this, then this is an endless loop it'll never get out of. And that's what the compiler will do. And so that's not going to work. So what we're going to do is use the word volatile instead. So what we're going to do is change, instead of just this guy, we're going to use the keyword volatile right there. And this is saying, hey, even if you don't think this is changing, assume that something else might change it that you don't know about. And again, do we need this casting on this side? Probably not, but it never hurts to do it. No, it turns out, even if you use no optimization, you still need to use this. Sometimes no optimization will tell the compiler, well, the compiler won't do it, but again, this is quite often needed, and it's going to be needed in some of the code you write. Without a cast, we'll give you a warning. Again, yeah, if you don't do this, you get a warning, but it should work fine. In most compilers, no guarantee that it'll always work. Okay, so Dylan's got some more information if you care to get that more data. So now what I've done, so either of these should work. Again, this one with a warning, it says right there. So now this new while should work. And let me show you what the assembly language now looks like. So the first two lines are exactly the same, but the difference here, program counter is right here, -2. It does go back to the beginning. Yeah, just because you say don't optimize, remember the compiler itself is a kind of optimization. So the people who write the compilers decide what levels of optimization mean. Anyway, okay, so this one will do the right thing. It'll keep reading this register each time it is doing the compare and then the branch. Okay, so you're going to need this. Okay, next step. So here's another example, and I didn't write this one. Wes and Chris, or Roz, and I forgot the other guy's name, wrote this originally. I think this was actually Wes and Chris. So they defined false and true to be 0 and 1. Then they have two unsigned ints. One's called course grade, and one's called impress Schwartz, which is either true or false. So how do you impress me? Well, you do well in the class. So here we got an endless loop while Schwartz is not impressed. That's what this says. While not impress Schwartz. So impress Schwartz starts at false. So the complement of false is true. So while true. So we stay in this forever. If you assemble this, this will be the equivalent to while 1. It's an endless loop. But what happens if impress Schwartz is changed? Yeah, O0 does not remove all optimizations. Compilers inherently optimize. Okay, so this, if impress Schwartz is changed in an interrupt service routine, again, the compiler doesn't know anything about interrupt service routines. At least it doesn't know that that runs kind of out of order. This looks like an endless loop. So let's look what we do inside the interrupt service routine. Here I said, okay, if the course grade is greater than 90, something gets us in here. Who knows what it is? Maybe a timer, maybe some external interrupt, whatever. It says, hey, if the course grade was greater than 90, then impress Schwartz is true, and that would get us out of this loop. again, if it's compiled away to this always being evaluated as a while one, you're never going to get there. So what you're going to do is you're going to make this and this a volatile. So if you make the Impress-Schwarz, you definitely have to make Impress-Schwarz a volatile. Course grade, since it's in this ISR, it may be that you don't, but the best answer is make both these volatiles, and then it should work. So if you make both of these guys volatile, this code will actually do what you want it to do. Okay, so that was volatile. I think there's some other things you might want to read in this lecture. I'm not going to go over them. These are some of those types that we're using. I don't want you to ever use these guys because those guys are very processor dependent, compiler. Well, these are understood by all compilers to be consistent. This is always a signed 8-bit integer. This is always an unsigned 8-bit integer. Int could be 8 bits, well, never 8, could be 16 bits, could be 32 bits. Long is probably 32 bits, and I guess could be 64 bits in various processors. But in any case, these are very well intended, what they need. And these are the ones you should be using. There's no ambiguities. Okay, float double. Again, read through this. It's not something I want to talk about. Okay, yeah, this is some of the stuff that was in the video. Okay, discard that. And next topic was oh, right. Okay, we're going to go. I'm going to change the share again. Share this screen and look at some of the documents. Okay. So first, let's look at the LSM document. Let's go to figure 3. Let me move this over so I can remember exactly what I wanted to talk about. Okay, so we're going to look at the timing diagrams. Okay, so first, this is a timing diagram for the IMU. First, let's look at these names. CS, that's chip select. If we're talking to this slave, then CS has to go low before we can use the SPI. So think of this as it's basically, hey, you want to use this or not? You want to use it, you need this go from high to low. And when you stop using the SCI, make it go from low to high. And then SPC is the serial clock. SDI is the slave data input. SDO is the slave data output. And so if you look at the clocks, where the clocks change, where the data is sampled, that's going to tell you what mode to use. Now, it says mode 3 here. That mode 3 is what it considers a mode 3. Is that the same as our X-Megas mode 3? Don't know, don't care, don't depend on it. Look at the timing diagram to decide which of the SPI modes for our X-Mega. And don't answer that question in Slack. I want people to figure it out for themselves. Now, something else in here, after this chip select goes true, we need a little bit of time before the clock should start happening. And so what is that? That's T setup. That's the clock setup time. So how much time is needed? It says at least 5 nanoseconds. At least 5 nanoseconds. Well, 5 nanoseconds is very, very fast for our boards. So in fact, if you make chip select go low and the very next instruction, you start the SPI system's clock going, you can't possibly do it that fast. So the instruction before you rewrite data to the data register in SPI can be making this pin go low. But you've got to make this pin go low, whatever pin you decide to use. So what pin should you decide? Let me see if I got a OneNote up here. OneNote. Let me move it. Oh no, I guess I can't do that, darn it. I'll go to OneNote later. Okay, so that's chip select. Let's look now at the 8331 manual. Let's find SPI. And let's now look for some timing diagram. Oop, there it is. So this shows all the little modes. Now this SS, it looks very much like that chip select. It has absolutely nothing to do with the chip select. SS is for slave select. Now if we're using this IMU S, this S means slave. The IMU is a slave. If we're using it as a slave, then that must mean the X mega is a master. So if we're using the X mega as a master, slave select doesn't matter at all. In fact, if you leave remember that all pins are by default input, if you don't mess with the slave select input, then you better be very careful that it doesn't go low somehow. Because if it goes low, it's going to screw up the SPI. A master's slave select pin, if it ever goes low, it says, hey, you're not really a master. You just think you are. And that'll be I think that's some kind of error. So what you normally do is you either keep the slave select pin low as an input and then tie it to high, either directly or through resistor, pull-up resistor, or you make that pin an output. And then you can use it as an output. And so it makes some sense to take this pin that's sometimes slave select and use it as an output and use it directly for CS. That just makes some sense. Okay. Okay, let's go back here. Timing diagram. Again, you're going to have to figure out which is the right timing diagram. Let's look at the backpack. This is the robotics backpack. And this backpack is slightly different than previous versions, much easier to use. So here's this guy right here and this guy here. These are switches. These are bi-directional switches is what they're called. And there's that chip select. From the IMU's point of view, Tim, the guy that made these boards, he called it CS to help with understanding from the IMU. And so that chip select, and there it is again. And there's a signal called chip select on the IMU. So what this guy is doing is connecting this thing that called serial in to, if this guy is low, then it's connecting it to MOSI, master out, slave in. If this guy CS is low, then the serial clock here is connected to SPI's SCK, serial clock. Now, if this is high and this is high, then it's doing what's called the I2C configuration. Because our IMU can do both I2C and SPI. And so notice this is the clock for SPI. This is MOSI for SPI, but this is also the clock for I2C, and this is what's called the SDA and SDI for, or the SDA for I2C. So again, if this guy's high, then we're using SCL for the I2C clock, and this serial input goes to SDA. So again, we're going to make these low. Every time we make these low, we make all three of these low, we're letting this chip do its thing. So that same signal, let's go back here again. That same signal, that's that same thing right here. When it's low, you can write to this chip. When it's high, that means I2C could take over, but there's no I2C connected, so nothing's going to happen. Okay, let's see what else we got to look at. So that's all I wanted here. And you can look at these spec sheets here. They are very, I don't like them very much. They're not very clear, but that's what it is. Let's go look at some more things here. Let's look at figure 9. Figure 9. Okay. I actually, it's a shame. I'm going to draw something that you can't see and then move it over. So I can draw it right here. Oh, I can't draw on that screen. I'm going to move things again to the other screen. Screen share. Okay, so I'm going to draw our X mega. You can see this, right? There's my X mega. Here's my IMU. So we have serial clock here, which is called on the other side SPC. Then I've got MOSI over here, is called SDI. I've got MISO, it's called SDO. And I've got slave select, which I'm not using as slave select. I'm going to use instead for this chip select over here. I'm going to use this as an output. This is an output. It's called slave select, but we're using it as an output. Okay? And then one more thing, this guy's going to tell us, if we want to know, it's going to tell us when something's done. So an interrupt, something can come back here. I call it on this side interrupt, and over here you can use whatever port X, pin Y, port X, pin Y, whatever pin you want for recognizing when this wants to interrupt. If you want to use the IMU's interrupt. Okay? Okay, so now SPI, somebody put on the Canvas thing, hey, SPI has a lot less configuration registers than a bunch of other systems. Well, there are, in our SPI system at least, there are less options, it's less capable. But in any case, there are still configuration registers. Well, the IMU also has configuration registers. And how many configuration registers depends on, well, let's find those configuration registers. Let me move this down here so you can see it. Move this away so I can see it. So I happen to know what the name of one of the, who am I? Who am? These are the configuration registers. Whoops. There's a lot of them. These are the configuration registers. Lots of configuration registers. One of which is called who am I? Who am I? Okay, so let's go back to that figure 9 I was looking at. So let's see what this is about. Well, each configuration register in the X mega, those configuration registers have an address. In the SPI, they have an address too. It's just we can't write to all those address bits at the same time. Here, we'll send the address bits through SPI. And so there are 7 address bits, so there could be 2 to the 7th or 128 configuration registers. I think there's less, there's probably more like 80 or 90 configuration registers. But that 8th bit, because there's always, things are grouped in bits of 8, is used, says here, read, write, not. So if this bit is a 1, that's for a read, which means SDI out. And if it's a 0, that's for a write, which means SDI in. So if we're sending, if we're writing an address, then the write will be 0. So if we're going to do an address, it'll be 0. So this who am I is a register we want to write to. Now, again, let me back up a bit. Here's our chip select. Again, we got to make this low before we can start doing anything. Now, if we're trying to read from a particular address, I'm going to put a 1 right there. So if I want to read from the who am I, let's go to the who am I again. Who am I? Who am I? Let's go to the top of this. Who am I has an address. Its address is OF, 0F. But remember that most significant bit is a 1 if it's a read. So if we're trying to read it, it's going to be 8F. And if we were trying to write to this, it would be 0F. So this is for a read. This is for a write. It turns out you can't write to this register. It's a read-only register. And if you read it, what you're going to see is this value, which looks like 6A. And if you have one of the old boards, I think it was 6.9. But you should have this board. So 6A is what we should read if we read from this address. Okay, so let's go back to that figure 9. I'll post this as well. So what we're going to do first is we're going to send to this guy, we're going to write to this guy the address, which was 1F, and we write a 1F to it. It's going to write, it's going to say, hey, that's the address you want to use. And then the next time we're going to write garbage, and we're going to read the data at that address. We're going to read, so we're writing this, so serial data in, so we're writing to this, these values, and then we're going to write garbage to the data in register, master out, slave in, slave data, yeah, and then master in, slave out, that's on the Xmega side, we're going to get the data at that address. So we're going to write to the data register twice. Remember, SPI's master, the only way anything happens is if you write to the master's data register. So the first time we're going to write the address with a 1 in this bit. And then the next thing we're going to do is we're going to write the data, some garbage, so that we can get the data at that address back. This is not unlike what I did for the LCD, that Excalibur LCD we did. First, we would say what little box of the 64 boxes I wanted to write a character to, and then we'd write the character. Anyway, that's how this works. And so what you're going to do, first, before you even deal with the IMU, you're going to write, I think in part 2 of the lab, you're going to write, you're going to send some data out SPI. Not even the IMU connected. We're just going to send data out the SPI. And you're going to connect your DAD to it, because your DAD can do SPI analyzing. And when your DAD analyzes it, you can see that I think you're going to send out a 37 or a hex 25, which is a decimal 37. So you're going to send some value out SPI, and you'll be able to see that with your DAD. And so you'll know your master out, slave in is working. And then the way we're going to see if the master in is working, we're going to connect, we're going to use the IMU, and we're going to write to the, we're going to read from the who am I register. And so we'll have then proved that the output SPI works with the DAD, and we'll prove the input for SPI works with the who am I. When that all works, then you can actually do the application.